Hello and welcome to Triple Index Queries. My name is John Snelson and I'm a Principal Engineer leading the Optic Engine team in MarkLogic. This is part 5 of a 5-part deep dive into the Optic Engine. We're going to be looking at queries against the Triple Index, and you will probably find it beneficial to watch part 4 at least, which talks about how the Triple Index is stored, and that storage then leads us to how we end up querying it. So do go back and check out part 4 if you haven't seen that already. But to recap what you would have seen in part 4, the Triple Index is stored with dictionary compression, where the values are stored separately to the triple data, and they're looked up by ID, and that plays a big part in how we then end up querying it. As well, it's important to recall that it is stored in a block structure on disk, and we read and write blocks at a time, and I need to decompress those blocks, reading from the start through to the end. Those blocks are cached, and that's what the triple cache and the triple value cache do. They cache blocks from the triple index and blocks from the triple value data as well. So we have a first in, first out policy cache for those, but the map, the index of blocks, triple index and triple value index, those are memory mapped into memory. They're much smaller files, has much less information there, and they help us to know which blocks we're going to go and search through and load from disk. So they need to already be in memory already. So this is a table that compares how the triple cache and the triple value cache work. Mostly they work very similarly, but there are some differences. So they're both D-node caches. They both just exist on the D-node where the data is. One reasonable difference is that the triple cache stores compressed blocks. So every time we read a block, whether it's in the cache or if it's come back from disk, we're going to decompress that. Whereas the triple value cache stores uncompressed blocks. When we load that from disk, we read through the values, uncompress them, and that's what gets stored in the cache. And the reason for that is because we need, to a much greater degree, we need random access into the values in that block. And the compressed data doesn't give us random access. These caches are both partitioned. That's a strategy for avoiding concurrency hotspots. And so different blocks will be loaded by different partitions of the cache, and the load gets spread out amongst those partitions. And when we do disk reads, we're actually doing disk reads of 64K rather than 4K, which is the block size. So we're loading 16 blocks at a time. And the blocks that weren't directly asked for are loaded into the cache, but they can be released from the cache earlier. And so if they're not needed by a subsequent operation, there's minimal overhead to having read those extra blocks. Both of these caches do grow and shrink in memory. They don't take up their full allotted amount of memory if they don't need to at that point in time, and they've got the ability to trickle release blocks from the cache if they haven't been used for a given time. Their timeout here, the default is 30 seconds. That is configurable, so that's the time at which a block that hasn't been used will be got rid of from the cache. Is there anything else to continue saying here? Yes, so they are both asynchronous caches. So when you go to the cache, you say, I'm going to want blocks 5, 7 and 10. And then you take a handle, and the cache will load those from disk in the background if it needs to, and you come back some time later, possibly then you might block, but we can do operations whilst it's being loaded before we need to block. Configuration wise, the triple value cache is a lot more randomly accessed, as I mentioned before. So that tends to need to be bigger. Their default configuration, I believe, is to a lot double the amount of memory to the triple value cache than to the triple cache. So now let's look at ways that the triple index is queried. One of the ways, and possibly one of the least used ways, that the triple index is queried is by using a CTS Triple Range query. That is an operator in the search query interface, or CTS query interface, and it can be combined with all of the other CTS query operators. And what we're doing here is really we're constraining the triple index based on the triple, the subject, predicate and object, and what's being returned is fragment ID and possibly positions. And this is actually the only time that triple index positions will be used if they're turned on, which they aren't by default. So given this query that you can see in the pink box here, we're going to constrain the red columns and the blue columns can be returned. The fragment ID is not in sorted order when we read it from the triple index, but it's then quickly sorted into sort order. And if we have positions, those are also returned. They're returned in a separate list. If you want to know more about how search queries work in MarkLogic, there are other deep dives into how they operate and what all the operators do there. By comparison, a call to CTS triples can pass in constraints for the fragment ID and actually returns the subject, predicate and object, the triples from the triple index. In this case, the positions aren't being used. Constraints can be put on subject, predicate and object, I suppose. So, but they're the things that are returned. In Optic and in Sparkle, it's much more as if the triple index is a 4-column table, where those columns are subject, predicate, object, and fragment ID. In this context, positions aren't used, and as I said, they aren't turned on by default. So you can have constraints against any of those columns, fragment ID, subject, predicate, or object. The subject, predicate, and object support conditions based on any of these operators that you can now see here. There is the inequality operators, there's existentially qualified equals, that's equivalent to an in clause, and then there's a not in clause, universally quantified not equals. There's also a range constraint which has greater than and less than at the same time, same term, which supports the Sparkle operation. And there's a bloom filter constraint, which we can't do apart from if their bloom join has been included in the query plan. In that case, that will use the bloom filter as a constraint against the column. As well as that, we saw the permutations or the sort orders that the triple index supports, and you can query against any of those permutations. The Optic Engine will choose an efficient permutation for your query to execute under, and that will be based on what the fixed predicates and information are about the triples that you're accessing, and about also potentially about what kind of sort order you want things to be returned in. And actually that sort order can be asked for both in ascending and descending order, so we can support order by descending as well. That's pretty much the only reason that we use descending order, because if you're grouping or anything like that, you just use ascending order. So here is an example of what you might see in the logs as a triple index lookup using this trace flag optic execution. So this is an example of a message sent to the D node to access the triple index. And you can see down in the table at the bottom the parameters of that query that this XML represents there. Now, the first thing we need to do when we want to answer this query against the triple index is we need to take those values in the query and we need to turn them into value IDs so that we can look them up in the triple index. So we take as an example the first name predicate here. We want to look up first name in the triple values and find its ID. So first of all, we'll look in the triple value index and we'll do a binary search there, and eventually we'll find the block that might contain the first name IRI. So having found that block, remember that block gets loaded into the cache and the cache decompresses it. So now we have what is essentially an array of values there. And we binary search again in those values to find the right one, and we may find first name and therefore figure out what its ID is, or we might not find first name. And if we don't find it, we know that it's not in the triple index. So that query is easy to answer. We can just return saying, yes, this doesn't exist. So let's say that we've done those value ID lookups and person 5 is ID 5 and person name is ID 3. So the IDs, so the query now looks a bit like this. So we've got a role set key of 0, or the first value, which is the predicate, is ID 3. The second value is person 5, that's ID 5, and we're accessing things in POS Permutation. So we've got the first 4 columns of the sort order of the triple index there to look up. And the triple index, which tells us which blocks to look in, contains information on those columns. So we do a binary search in the triple index and we figure out which block it is that we're going to need to read to find triples that might match that information. And when we figured out which block or blocks that it is that we need to scan, we load those blocks up into the cache and we decompress them and scan them for the correct information from start to finish. Remember that we always have to decompress from the start of the block, so every block is read in its entirety. But we've got run length information in the blocks. That tells us, for instance, that there are, in this case, 5 role set keys of 0. 5 rows with the role set key 0. We know that we're looking for role set key 0, so those 5 rows match, but we see here that there are 3 with value ID of 2, and we know that we're looking for value ID of 3, so we can skip those 3 rows and jump ahead knowing that they don't match. And then again, we know we're looking for PSO, which is a 0, so we know we've matched there, but the second value ID, we're looking for 5, and this row that we've just come across is a 4, so we can skip 1 row according to the run lengths. And then we find a row that does actually match the information that we've got, and we can start returning that from the triple index. Now, having got these rows out of the triple index, we still have value IDs, and we need to do a reverse lookup to turn those value IDs into the actual values before they're returned to the user, returned back to the eNode. So if we've got value ID 8 here, we need to figure out where that is. First, figuring out which block it is. So we can do a binary search in the triple value index to find out the block that will contain value ID 8. And having found that, we can jump straight to value ID 8 because it's random access. Then at that point they're decompressed for us. So then we can fetch value ID 8 and add that to the result, and potentially then do more operations on it or return it to the eNode, as I said before. So that's the basic overview of the execution of any kind of query against the triple index. As well as simple triple index accesses, there's also the row accessor, which is a special purpose operator that can return rows extremely quickly for tabular views. So in this case, we've got a row accessor. We can see the query there in the table at the bottom of the slide. We're accessing several columns, 3 different columns. We've got a constraint on the rows, and that constraint really says any row ID from this particular table. So between the lowest row ID and the highest row ID for this table. And in this case, we're accessing in a row-oriented fashion. That is the SOP permutation, where the major sort order is the row ID. If we think about what that looks in the triple index, that means we're selecting a region based on S, the subject, which is the rows, and that goes from the lowest row ID to the highest row ID. So that the only thing in that region of the triple index is rows for that table. So that is a very efficient way to access the table. And in addition, each row, all the values for a given row are together in that index. So we can read off all the values for a row and then return that row, start with the next row, read off all those values. Another way to access rows that the row accessor supports is a column-based or column-oriented row lookup. In this case, we use a different permutation. So this is a PSO permutation. So P being the column ID means every value for that column is together in the triple index. And we do a read of several regions of the triple index, much smaller regions usually, that only contain information for a given column. We stitch those columns back together based on the row ID. And if you have got a very wide table and you've only selected a few columns from it, then a column-based access can be much more efficient because we're reading less of the triple index, only the columns that were actually asked for. Now we also store a permutation that's equivalent to a column index in a relational database. So that is the POS permutation. So P predicate is the column ID. So we're selecting data based first on column, but then O is the value. So that's a column sorted first by value and second by row ID, so hence a column index. Now in this case we may want to use a column index to reduce the number of rows that we need to fetch because there's a constraint on the book ID column. So this book ID must be equal to trader 07, and to do that we simply use a scatter join against the row lookup accessor for the whole table or for the remaining columns. If you recall from part 1 of the Optic Engine deep dive, a scatter join does sideways information passing. So the rows from the column index are gathered and sent through to the right hand side where they're used as a constraint to reduce the number of rows that need to be looked up in the row lookup accessor. Another way to use column indexes is to order the table by a certain column. And in this case, we do a hash join of the row lookup accessor against the column index. And because the column index returns things in value order as they're looked up in the hash table, the whole query then returns that table in the same order as the column. Now we saw the Optic Engine architecture back in part 1 of this deep dive, and we've looked in that part at the E-node operators and things that operate there. And we've seen a little bit now of the D-node operators and what they do as they access the indexes. But when we're accessing the D-nodes, we have one E-node, one place where their query starts executing, but attached to that are multiple D nodes, and they all need to take part in answering the queries. And those D nodes have one or more forests on them, and each forest has a number of stands. And stands, you'll recall, are the things that get merged up inside forests, but they each represent a sorted list, a sorted section of the triple index. So when we query, we need to query each of those stands, and we use a MapReduce style of algorithm to do that, so that each stand has the map operators executed on it, and then to combine the information from each of those stands, we use a reduce step. So when we're executing these queries, we start on the E node, and we encode the message to the D node and send that out to all of the D nodes. They're going to decode that message, run the map operator on every stand, and then they're going to reduce the information from those stands. So for a D node, all of the information from all of its stands gets reduced to a single answer, encoded and sent back to the E node. Now the E node now still has multiple responses from multiple D nodes, so having decoded those, it's going to run the reduce step again, and finally be able to give the answer that was intended from that query. So what are the reducers in MarkLogic? If you look at the Optic execution output, you can see a little section here highlighted in green at the bottom of the call, and that is the reducer that's going to be used to combine results from the D nodes, from all of the different stands on those D nodes. In this case, this is a Sparkle query, and the standard Sparkle semantics is to deduplicate and remove duplicate triples. And so in this case, it's doing an ordered no dupe result, where it maintains the order of the triples and uses that ordering to deduplicate them. Now, an ordered return result is not the most efficient reducer. The most efficient way to return things is unordered, and the deduplication does cost a bit. So if you are using Sparkle, you may consider turning that deduplication off with the dedupe equals off option. And actually, that allows us to be a lot more efficient and allows us to push down a lot more operators to the D node when you're executing Sparkle. So here's an example of an unordered reducer, and in this case this is a row accessor which is being returned unordered. So the rest of the query doesn't require a particular order of it, so it doesn't matter which order things come back in. And you may actually notice that depending on the day of the week and how your data is and what merges have happened and what order the cluster booted up in, you may get the tables back in different orders if you're not requesting a specific order. So in that sense, don't rely on the order of results from Optic or SQL or Sparkle unless you have specified an order by in your query. And the full list of different reducers that MarkLogic supports are here. So there's ordered, unordered, and then ordered. Ordered does a merge sort, so it takes several sorted lists and merges them into a single sorted list. We just looked at ordered with deduplication, but two that we didn't look at are sort-based grouping with aggregate calculation and hash-based grouping with aggregate calculation as well. And although those reducers take more time, they're faster than doing that grouping on the E node, so it's actually a good thing if the grouping gets pushed down to the D node. So to recap about what we've just learnt, we've looked at the triple and triple value cache, what they store and how they store that. We've looked at the different operators that are supported by the triple index that can actually be used to reduce the amount of data that we read from the triple index. We've looked at value and index lookups via the block indexes and how that works. And we've thought about the row accessor and how that can return rows faster using row-oriented and column-oriented data from the triple index. we've looked at column indexes, and the row accessor and the column indexes are really benefiting from the permutations that the triple index supports. So you don't need to define a column index. There's a column index defined on every column from a table in MarkLogic. And then we looked at the reducers and how they work and what their role is in combining results from the dnodes. Thank you for listening.